Our next speaker is Chris Rowen, and his talk is Taming the Beast, Performance and Energy Optimization Across Embedded Feature Detection and Tracking. Out of curiosity, do we have any engineers at all in the audience? Right? A few, right? How many of you have had to optimize anything? Right? How many of you have ever had to deal with trade-offs? Right? This is the core of what we do as engineers, and this is exactly what Chris is going to be talking about today. Chris is a fellow at Cadence Design Systems. Prior to that, he was the CTO at Tensilica, which was acquired by Cadence. He's a veteran of the semiconductor and high-performance computing architecture and electronic design automation worlds. He helped start MIPS back in the 1980s, and this is going to be a great talk. Chris?
All right. Thank you very much. I'm really going to walk through a set of interlocking issues. One of them about some of the fundamental challenges of imaging and vision computation, and one of them really about optimization, particularly when you are obsessed with the questions of performance and energy. And that's centrally important as we try to take all this great concept and demonstration of vision capabilities and put it into our everyday lives. And in fact, there are lots of places where this imaging challenge comes through. It obviously is happening in our mobile devices, in cameras, in the broadest sense of the word. It's happening in improving those images to take great pictures, but it especially is happening when we try to make intelligence out of those things. In general, consumer computer vision, and in automotive applications, and in applications where we're really trying to push the envelope on the level of cognition as well as the level of performance that's taking place. And our ultimate goal is to create platforms where the creativity of a wide variety of developers can be focused on optimized silicon solutions that allow people to get those new kinds of applications into the market very quickly and have them work in everyday mobile battery-operated systems. So energy keeps coming up again and again as one of those places where we're just going to get very passionate. But let's look at the total imaging chain, because one of the things we find is that the requirement for image processors and image software is going to be most especially emphatic at those places where performance demands collide with complexity of the algorithms being done. So if we look down this pipeline from the hypothetical sensor at one end through single frame image signal processing into multi-frame image enhancement, smart photography, image and video analysis, and vision, into encoding, storage, decoding, and post-processing, we find that there are some parts of the problem which are relatively straightforward, and in particular relatively stable and lend themselves to hardwired or substantially hardwired solutions. This tends to be very true for encode and decode, where the standards evolve really rather slowly. Once every 10 years we have sort of new encoding standards appear. And it's somewhat true in the front-end ISP, though that is fracturing even today. But it is most especially true in the image enhancement and vision areas, and to some degree in video post-processing, where there is this collision. And you have not only high rates of computation, but high rates of change in algorithms, and really lousy memory locality. So it's a grand challenge problem generally. And so what we're going to find is that people are evolving their solutions from things that were once hardwired to more programmable because the complexity is rising, and from conventional CPU implementation to more optimized implementation because the frame rates are growing, but at the same time the target power for the platform is shrinking dramatically. Excuse me. So I'm going to first take a look at some of the elements of the gesture recognition pipeline. And I can't talk about all of these things, but I'm going to talk especially about two steps along the way. One is bounding box computation. This is connected component. This is labeling, where we want to identify the kind of the large objects of interest to be able to then classify them or track them from frame to frame more easily. And then I'm going to look later at some of the feature detection pieces that go with that. So now let's think about this pipeline. And typically what we're going to see is some image which passes through some denoising, background subtraction, go through some morphological operations like dilate and erode, then do connected components where we're going to try and find what are the blobs of stuff in this image which are in fact part of the same object as opposed to different objects. And that will allow us to finally do a reliable bounding box computation. These images, by the way, are taken all from our reference OpenCV implementation of this whole flow with significant optimizations on our target platforms that allow us to get quite efficient implementation. Another way of looking at this computation is we're going to take some image like this reference image here, and we want to identify that each of those different shapes is in fact a different shape and find all of the connected elements, all of the pixels that make up that element. And to be able to apply a unique label to each connected component. Now, in order to do that, we will sort of search from each component, from each pixel, to find all of the ones that are adjacent, looking at 4 or 8 neighboring pixels. And then we're going to apply labels. And since we want to search in parallel, we're going to find that as we have partially identified some object, we may find that that when you reach a boundary to another labeling, you'll say, oh, okay, these two objects touch, so they're really one object, and so I'm going to have to substitute labels in order to get the smallest number of labels possible. And there are both two-pass algorithms and single-pass algorithms, where single-pass algorithms typically will propagate information to identify connected components and then merge the maps to get the minimal set of labels associated with it. And that has some significant advantages because it does lend itself to vector processing, data parallel processing, though it's computationally hard unless you have the right kind of vector processing capabilities. And in particular, you have a set of operations that you may do as, for example, you operate on vectors. And here I'm assuming some vectors really representing a horizontal set of contiguous pixels in my image, where it's actually relatively easy to go figure out, well, from a given vector, what of the pixels below that vector are in fact connected to it. Just testing adjacency by looking down and left and right. What's trickier is to figure out, as you propagate across a vector, what are the adjacencies. This is easy in serial processing. It's just that move to the left, move to the left, move to the left, or to the right. But if you want to do it in a vector processing, you actually want to have instruction set primitives and operations that allow you to propagate horizontally across an arbitrary length vector to know where you have contiguous pixels and where there are breaks in that. And so this is something which tends to drive unique characteristics in vector architectures used for image processing compared to vector processing of other kinds. And it's one of the driving forces behind architectures for image processing. You also have this relabeling pass, where relabeling is a kind of a lookup operation. Because as you have gone through and identified labeled connected regions, you found adjacencies between connected regions, which said, label 1 really is the same as label 2. And so that creates a remapping, a renaming table. But then when you go through the image on the second pass, you need to look up all of those things and rapidly relabel all of those objects, including being able to relabel multiple objects per vector. because you could have almost an arbitrary number of relabelings that happen to occur within a single vector. And so having fast lookup capability that allows you the flexibility to do many renamings per operation becomes critically important to performance and efficiency. So we've applied these techniques in building an optimized connected component package for our platform, and using some standard pedestrian databases, in this case computing rapidly the bounding boxes as a reference implementation. And with a small amount of effort in optimization, we got 30 to 40x speed up in the labeling performance relative to a fast RISC implementation of equivalent code. Now I'm going to take a very quick look at some other pieces of this puzzle, in particular looking at feature detection and the range of different kinds of feature detectors which are at work. There are so many different kinds of feature detectors we could spend all day comparing and contrasting them, but I'll give you just a little bit of a glimpse of some of the computational characteristics associated with the feature detection pipeline. One of the things that is noteworthy is that there is a very big difference in the computational demands at different points along the feature detection flow. It's kind of a funnel in which you start out by really wanting to create the feature response scale space to search for the basic key points. And here you're going to use things like difference of Gaussians as ways to identify candidate features. And that can be done in a highly parallel fashion, and that's where you're really working on the raw image. There are not yet any points of interest. You don't have anywhere to focus, so you have to compute on every single dang thing in the image. And so you're typically going to be operating on as much as millions of pixels per frame. And if you're doing this operation at video rates, you're going to be talking about potentially hundreds of millions of incoming pixels per second. And then you go into a stage where you're really operating on finding points in the extrema, in the scale space response. So now you're sorting out which are the kind of the embryonic features of interest, which is usually a kind of min and max detection algorithm. And then you go into feature localization, where now you have real candidate features coming along, and you want to localize them by essentially looking at all the way down to sub-pixel resolution over the exact geography of those points. And those only have to be done on the number of candidate features. So you now may at this point have gotten down into hundreds or thousands of points of interest per frame. And then finally you get to feature descriptor generation, where you're now sort of capturing the appropriate invariance of that set of features in order to go then into the classifier or into the further mapping. So this set of things comes in the form of SIFT, often used in this difference of Gaussians computation, typically operating on fairly low resolution data, typically operating with things like symmetric filters, so kind of classic hardcore signal processing functions. Then SURF for really calculating feature response. This is where things like integral image, which is typically a very high resolution computation. So we have to move from 8 bits often up to 32 bits. And FAST, which is using pixel intensity comparisons to find points of interest. And this may drop you down again in terms of resolution. So one of the things we find is that if you're really trying to be energy sensitive, you're going to adapt the resolution of computation up and down during different phases of this computation. And so a good architecture as a target is going to need good support across a wide range of different types of computation. It needs to be good at scalar computation, it needs to be very good at vector computation, it needs to do 8-bit, 16-bit, 32-bit, sometimes even variable resolution, floating point-like computations along the way. So now we can start talking about some of the issues when you want to map into a vision DSP, where you're not just thinking about algorithms, and algorithms are important, and the best algorithm, improvements in algorithms will always beat improvements in the underlying processing architecture. But once you've settled on an algorithm, you then need to figure out how you're going to map it. And three of the really key issues in mapping to a platform is how are you going to exploit data locality? And data locality is incredibly important because the energy consumed in fetching memory can, if done badly, completely swamp the energy of computation. If you don't exploit local locality and you have to go off chip to DDR for every pixel, your computational rates will slow by an order of magnitude or two, and your energy will increase by an order of magnitude or two. And so there are a whole set of techniques in a modern platform in order to do that. We have achieved quite broad success now for IVP and now IVP EP platform, which is become used across games, televisions, smartphones, tablets, has really developed not only a broad uptake, but in particular has developed a large body of software with many hundreds of library elements, third-party applications, and developers around the world who are targeting the IVP platform. And that's an important thing, to be able to have this aggregation of interest in a platform where you get this virtuous cycle of adoption, which lowers the programming effort overall. And finally, there are a number of key tools in tuning, which rely on being able to model in a multidimensional way what's going on in a system, all the way down to a pipeline view, to do memory analysis, to do compiler-based optimization, and even to do instruction set architecture extension, sort of on the fly in the development of products, but yet still leveraging this kind of more universal architecture view. So in IVP EP, we took some of those lessons learned in those advanced feature detection and connected component and a large body of other applications, and built it into the evolution of the instruction set architecture. So you see in that architecture the 2 to 4 times increase in a number of key parameters, like the scalar performance, the 8-bit performance, the 32-bit performance, symmetric filter performance, and data reorganization on the fly, all increase fairly substantially, because we're finding that that's important to not just driving up performance, but driving down the energy. And then let's look at what it means to analyze the energy. And this is an important part of driving into the high volume space. Even if it's not strictly speaking running on a small mobile battery, many of the characteristics of success of a product are directly correlatable to the energy it dissipates, even if it is once in a while plugged into the wall. And so what you find is that in moving from a conventional, let's say a RISC implementation, to an optimized implementation, you have a huge opportunity to drive the performance up and the energy down quite significantly. So I'm using as a baseline a very low energy RISC cores, one of our entry-level RISC cores, which is pretty good at this category of fixed point computation. But moving it onto the IVP platform gave us between 30 and 35x improvement in this whole suite of things around the connected component computation, which mixes together both vector and scalar computation. But at the same time, we improved the frames per watt rather significantly. Of course, the IVP platform is significantly bigger than this ultra low power RISC core. And so the performance increases more than the energy improves. But nevertheless, you see improvements in both the core energy dissipation and the memory power. And I want to focus on the memory power for just a moment, because going to this kind of an architecture dramatically reduces the amount of both instruction fetch and reduces the data fetch energy by a significant margin. So you're getting about 12x improvement in memory energy, about 6x improvement in core energy, netting out to something like about 7x, 6 to 7x in overall energy as a result of this optimization. And that's the result of having architectures and tools which allow you to measure these things more precisely and to drive the choice of optimizations around these energy goals. So to wrap up, there are a set of lessons learned. And first of all, one of the important things is that there are more than enough interesting hard problems to work on. And the algorithms are very diverse in structure, and they are evolving very rapidly. This morning's keynote was a wonderful example of how in the last couple of years, the whole recognition pipeline has fundamentally changed. And those are the kinds of algorithms which are now being mapped onto these low energy implementations, because we want to do all the things that was talked about this morning, but now do it in a few milliwatts. I think you have this hard balancing act between wanting ease and agility of development, to be able to introduce completely new algorithms in a matter of days, but at the same time having these ultra low energy results, which is often in significant tension, because the conventional way of getting to low energy is say, well, let's build a hardwired piece of logic to go do that and map it into the most advanced custom silicon process. Well, that takes not days, that takes many quarters. And then you find there's just a whole lot of things that matter in a big way. The tools matter, the target architectures matter, software and especially libraries matter enormously, and good software engineering so that you can handle the complexity of these things. They can move swiftly from high-level modeling, for example in MATLAB, all the way down to optimized code over the course of weeks. So when I was here last year, I talked about a code tuning checklist. And here I've expanded that test list because my team and I have invested massively in porting a wide range of different applications onto this category of platforms, and can really, I think, speak to the blood, sweat, and tears that goes into really pushing the envelope on energy and on performance. I leave that for you to look at. I think that some of the key things are really being able to understand how to stay at a high level in programming, yet exploit some of the optimized features that are visible to the compiler and the software to be able to do it, and to have really a continuous feedback loop of measurement and optimization to drive the solution. And finally, I leave you with some resources about this category of processors, about connected component labeling, SIFT, SURF, and FAST. As well, I welcome questions at this point if we have, we have some minutes. Good.